Thanks for joining me for Proposition 7.8.1 on the properties of joint CDFs, cumulative distribution functions. Let x and y be joint random variables with joint cumulative distribution function, capital F of xy, and let a, b, c, d be real numbers. First property, the probability that a is less than x is less than or equal to b, and c is less than y is less than or equal to d is f of bd minus f of AD minus f of BC plus f of AC. So that looks quite random. It looks strange and hard to remember. There's a little memory trick for you. Here, when you have the two largest terms together or the two smallest terms together, here, then you have the two positive terms. And if you mix and match, so if you have a small term with a large and a large with a small, then your terms are negative. So that's a little memory aid. But better yet is to understand why this is true. And to understand that, let's draw ourselves a little situation in the plane. And if we want the probability here, then we're talking about the probability associated with a rectangle. So let's draw in a rectangle from A to B in the x-axis and from C to D in the y-axis. And so what we really want is the probability associated with this rectangle. We want the probability in there. Now, if we do f of BD, yes, if we do this one, f of BD, well, that's everything that is below D and below B. So we're getting the region that we want, but we're also getting way too much. And so we need to kind of subtract some stuff off to get rid of that. And if we subtract off, well, AD, f of AD, well, AD is here. And so we're subtracting off everything below D and everything below A. So we subtract off the right piece, but not all of it. So we also need to subtract off down here. If we subtract off f of BC, well, BC is here, so everything below C and everything below B, then we get that last missing piece. But unfortunately, we also take this off down here. And if we look in the bottom right corner, we've subtracted, well, we added that in once, but we subtracted it off twice. And so we have to sort of add it back in once to make it even, to counteract our extra subtraction, and that's what we're doing here. F of AC is the probability associated with this lower left corner, and then we end up with just the probability associated with the rectangle that we want. So that's why that expression makes sense. Property 2, f of infinity infinity, which is a shorthand way of writing the limit as x goes to infinity and y goes to infinity. And by infinity, we're really meaning the maximum values in the support of each. So they may not go to infinity, but they may go to some constant number, some fixed number, and that's what we mean by the infinity, the largest value in the support. And so that is, well, that's simply 1. And to see why that is, let's remember what the definition is. F of infinity infinity would be the probability that x is less than infinity and y is less than infinity. Well, x is always less than infinity and y is always less than infinity, or less than or equal to their maximum values. That is always true, and so the probability is 1. Third property, f of x infinity or f of infinity y. Those end up by giving us the marginal CDFs. So f sub capital F sub x of x is the marginal CDF for x, and over here we get f sub y of y, the marginal CDF for y. So to see why that is true, well, again, let's go back and look at what this joint CDF means. That's the probability that x is less than or equal to x and y is less than or equal to infinity. Well, y is always less than or equal to its maximum value, or less than or equal to infinity. So that is really just the same as the probability that x is less than or equal to x, and that is the CDF for x. And the exact same explanation works for the CDF for y. And the last property here, if the x and y are continuous, right? So everything above worked for discrete or continuous. Now we're looking at just the continuous case with joint density function small f of xy. Then the joint CDF can be found by integrating. So from minus infinity to x, from minus infinity to y, which means we need some dummy variables in our integral. So f of uv, and the order that I've written it is dv du. And if it is an integral, then the small f, the density function has to be a derivative, and we need to differentiate in both directions. And so we're talking about del squared f del x del y, or del y del x if everything is continuous. The order doesn't matter. It is the second mixed partial of the joint density function. So in the next video, we will go and apply some of these properties.